Okay, I think it's time to go on to the next paper. This next paper is Applications of Quantum Annealing to Music Theory. And this will be presented by Ludmila Botelho, Fabiola Cañete, and Ashish Arya.
All right. So, hey, Fabiola, could you share your screen and give me some powers? Okay. All right. So everybody can hear me well? It's everything okay? Can I start? All right. So thank you everybody. Thanks for showing up for this presentation, and thank you the organizers for inviting us. Today, I and my colleagues, we are going to talk about a project we developed in the summer for Keyword. So my name is Ludmila. Nice to meet you all. And our team members are basically Ashish, Fabiola, Dhruvi, and our supervisor, Özlem. So, okay, let me give just a brief outline because I'm going to present the half of the presentation. So I'll give you some insights about quantum annealing and optimization and a project that I'm working by myself, which is music reduction. And the follow-up is going to be the counterparts generation by Ashish. And then music completion using Markovian random fields with Fabiola. Okay, so let's get started. Quantum annealing. Well, it's well known that lots of interesting problems can be boiled up as optimization problems. And one could be wonder like, what if a salesperson want to visit in the most efficient way a set of cities? That could be boiled up. And this is a particular hard problem. So that's why we have some motivation, for instance, looking at other kind of computation instead of classical stuff and looking for quantum computing. But not just regular quantum computing. Here we are going to talk about quantum annealing, which is it's being implemented by mostly like D-Wave machines. And for this project in particular, we'll be using a bunch of a set of tools provided by D-Wave called ocean tools. Anyway, so what is about quantum annealing? Basically, you want to shape our problem as an energy minimization problem. So we want to find in the energy landscape which one is the lowest point inside of this. So it's different from the gate-based computation, because on gate-based, what we're going to do is to take the qubits and apply the set of operations, a set of gates, like pretty much as computer gates, and in a linear sense, pretty much as a circuit, and find some answer. For our case, this is going to be different, because what we're going to do is to prepare our qubits in a superposition, which is control by an operator we call Hamiltonian. This is a term from the physics. And the initial state, which is going to give like a preparation is going to be given by this H0 here, is an easy one. It's something we can easily control. And we want to move this adiabatically, with a certain time for the proposition we want to search for, like the problem we want to shape, which is this HP here. Again, like this Hamiltonian is just an operator that says that it says about the forces we're going to apply to a system to move to one state to another. Okay, and again, this problem, to shape this problem in this Hamiltonian, using this Hamiltonian into this operator, we need to shape this as a quadratic unconstrained binary optimization. And the solution of this problem, the ground state, the lowest energy state, is what we are looking for in this landscape. So again, just to exemplify to guys get some flavor about this. So we start our problem with a superposition, for instance, 0 and 1 qubits. And then we apply some magnetic field to make some distinguish between them. And the thing about this, the interesting feature about quantum annealing, the quantumness, is the possibility of tunneling from like these valleys of energy, so we can move to this configurations of lowest energy without much cost. Anyway, so the quadratic unconstrained binary optimization by itself is just a method we're going to minimize some quadratic functions. For instance, given like this, we have a set of binary variables we want to minimize with some constraints. And this constraints, to make this function more interesting, give more flavor about this, we have to pay attention. We can add constraints and penalty. Why? For instance, let's suppose we want to minimize a certain function, y, and it has a very interesting constraint, such as like x1 plus x2, it has to be less or equal to 1. So one of the variables must be 1 or 0, at least. Both of the values, if this is violated, this is going to give some increase, add some value, some penalties. And in our case, this is interesting because when you add some value here, when this constraint is violated, it means you increase the energy of the solution. And this is undesirable. So again, since we are looking for the lowest point, this is probably not going to be selected. Anyway, the problem, so I'll give you some flavor about this, what I'm talking about. Let's move from the math or actually music stuff or whatever. So my inspiration for this project was basically like, I don't know if you guys know this, but I'm really a fan of video games. So I always wondered like how old video games could encompass so much details and awesome stuff about music and graphics. Nowadays, video games can do pretty much everything, but old ones, they have to take care about this compression. And from this is not a bug, this is a feature. A lot of culture arises from this. People are literally plugging video games to make music. I think you guys already know about this. And why I was talking about this? Well, because since they have to encompass very simple wavelengths, wave shapes, and in a very small set of channels, I was like, what if we take a very complicated song and try to reduce this? So yeah, music is very complex. There's a lot of things going on most of the time in this orchestra. There's many instruments, but there are some features we can perceive, like something like the melody, the rhythm. Pretty much everybody with their own brains and hears everything is functional. We can perceive some stuff in common, like and we can identify if the same song is played like in a piano, is played like an orchestra, and so on. So from this, I was wondering, we can make, there is some previous work about this, which is called phrase identification, which is like given a set of sequential notes, we can identify some stuff inside. Like for instance, as I said, the melody, the foundations, baseline, and we can segmentate the songs according to this. This was made in the previous work about the track segmentation, but the problem is how to select, to make this arrangement, this reduction in a very interesting way. There was, as I said before, this was made classically, but why not quantum? Because this could be a very difficult problem. For instance, for the problem that I want to work, I want to reduce, for instance, we have like this 4 tracks here. I want to reduce for half of it because I don't have much space on my video game. So, and there is a problem because if you select one of those tracks, for instance, let's suppose like just one, there are some overlaps between them. So this choice can lead for very complicated combinations. Like for instance, if I choose this first yellow one and move to this red on the bottom, this is not possible because they clash. And this is not desirable. We want to make our music still linear with most of the correct tempo and the sequence. It must be sequential, but this could be troublesome and computationally challenging. So what is relevant? What I want to select? Because since we need to minimize this problem, we want to take the most information we want. For instance, I was wondering like, okay, let's suppose we have this track here. It's just a repetition of 2 notes. It looks like pretty much something on the background, like just dun, dun, dun on the background, right? But this other one here looks way more interesting. There is a lot of variation on the length of the notes and the fifth. This looks probably something that has more, information by itself. So to shape this problem after this track segmentation, it's made classically, we can think about this. Let's suppose like these phrases, the segmentations, we can define this as a set of binary variables in such a way, like it is a phrase selection. This is binary variable xyj selected. It's set to 1, otherwise it's 0. And consider this information for the phrase. We're going to encapsulate this as a measure of entropy, which means like basically I want to, for defining this, we consider the variation of the fifth and the rhythm in a set of notes. And what we want is to maximize this information. So we want to apply, like as using this as our objective function, the summation here, when we have like, given a certain phrase times its entropy, we want to maximize this quantity. And what I say again, like about the information, is literally Shannon entropy. So basically, it's the how much surprise you get from something, which is like the logarithm times the probability. The lowest the probability, the biggest is the surprise. Anyway, but again, the constraints is very important as well to shape our functions, to make this to shape this in a way we can get our desirable output. And for this, we wanted to consider something like the music can stop, right? So we're going to select some phrases and make it sequential. So we divide this phrases as according to the measures of the song, literally the measures. And if the phrase is selected, it's equal to 1, the measures inside are equal to 1 as well. And this is a hard constraint. And then we want to sum up for a certain timestamp because we don't want too much overlap. We want to reduce these things. For instance, like this M, which is the number of the tracks after reduction, we want to select in such way everybody's going to be set at 1, all the measures. Like we want to sum it to the number of tracks. We're going to reduce. And of course, with this value, we want to make this for the full song. So yeah. From this, my mouse is not working. We try to make an attempt using a hybrid solver from D-Wave. And let's try to hear. Okay, but as you can see, there were some problems here. Because of this formulation, there is still some kind of empty spaces. And what we guys basically listen to, it's what the algorithm thought it has more entropy. It was more interesting. But yeah, in some points, of course, we have some clashes and dissonances, but we want to solve this as a future work because, of course, just because of a lot of entropy was selected doesn't mean that two new tracks are compatible. So we have to formulate like some sort of dissonance criteria. And also, let's suppose we want to make this new adaptation, not just for a video game or whatever, we want to make for a flute and a guitar. So some of the tracks, the selected tracks can also be problematic according to the initial constraints for the new adaptation, new arrangements you want to do. So this is it. Thanks all. And let's move for our next colleague. Please, Ashish, come here.
Can I have the controls? Let me check. I think I can control it. Yeah. So this is Ashish Arya from New Delhi, India. So I'll be presenting my part of the work on counterpoint generation using quantum annealing. Counterpoint is a technique of musical composition. It was very popular in the Middle Ages. So basically, counterpoint literally means a point against point. So in musical terms, it will mean a note against note. So in counterpoint, a musical track is given, and based on that musical track and certain rules, another musical track or more than one musical tracks are composed. So actually in the music theory, counterpoint comes in different kinds called species, first species, second species, and so on. First species has one note against one note, second species has two note against one note, and so on. The fifth line is also called as cantus firmus. This is the term I'll be using several times in the presentation. So before moving ahead, let me just play an example of counterpoint music. So this was a simple example of counterpoint music. Actually, counterpoint, particularly I'll be dealing with first species counterpoint. It is based on certain rules. These rules have been developed historically by great musicians. But one specific issue with these rules are different musicians in different era have devised their own counterpoint rules. And these rules have hierarchy among them. Some rules are sacrosanct and it is common across all the music teachers, but some rules are flexible. Like if you break this rule, you have to do this. And if you break that rule, then it can be compensated for, things like that. So I am using a counterpoint rule known as standard rules. Let me also briefly mention the previous work done in this field, particularly the work by Mazzola and other researchers in the field. And the last one is by a person known Piotr Martysik. I am using these references also in my problem solution. So I want to solve counterpoint generation problem using quantum annealing. So I have defined my problem, basically a generation of sequence of nodes based on a given node of countertransformers and using D-wave quantum annealer. I have made certain simplification assumptions, like my counterpoint track is going to be in higher pitch, that is, it is going to be above countertransformers. Further counterpoint is going to be in treble clef, and I'm using only whole nodes. So what is my approach? First of all, counterpoint is generated in sections, like a large piece of music will be divided into several sections. These sections are already decided by the composer. Then I'll take a section of the given track, the countertransformers, and I'll generate same number of nodes for the counterpoint. For example, here I am taking a section of 9 nodes. So each node from N0 to N9, N0 to N8 will be used for generation of counterpoint music. Given a particular node, let's say the first node N0, I am going to have 27 possibilities, 27 possible pitch values for the corresponding node in the counterpoint music. So this 27 comes from the counterpoint rules, and I will model it as a binary variable. If particular note value out of these 27 is going to be present in my output, in my counterpoint, that particular binary variable will be 1, otherwise it will be 0. So here I have 9 nodes and 27 possibilities. So I'll need to total 243 binary. I think it's not moving. Yeah. Problem, I need to introduce the rules of counterpoint music generation as constraints of the Cubo optimization problem. I'm just giving one example of the several rules of counterpoint. That is about the first note of the counterpoint music. This rule says my first note has to be either in unison or perfect fifth or octave with respect to the given note in the countertransformers. So as you can see in the equation written below, I am filtering out those notes which are at unison, perfect fifth or octave. Like I am taking J as 0, 1, but 2 is not there because that is at unison or perfect fifth or octave, and so on. So these notes are actually the notes which should not be there in my final music. So I am penalizing them at a penalty value P1. Similarly, all the constants are modeled as all the rules are modeled as some constraint for the Cubo optimization problem, and their specific penalty values are chosen. These penalty values, selection of these penalty values are like feature selection of an optimization problem. So I set up the problem, run the Cubo optimization method. The minimum value, minimum energy value solution corresponds to my solution, corresponds to the counterpoint generated. And this is the graph in the right side also showing how the energy value decrease as more and more constraints are followed. That means as the counterpoint becomes better and better in terms of the music generated. Let me also mention I am using certain negative penalties that are awards because that's how the counterpoint rules dictate. because some notes are going to be awarded because I prefer them to be there in the music. So these are my results. Here I have 3 music pieces. The below one is the input transformer. This is the fixed line against which the music is generated. The middle one is the human generated counterpoint, and the top one is the algorithm generated counterpoint. So let me just play it. So let me play the human generated counterpoint. Now the cubo generated counterpoint. So that was about counterpoint generation using quantum annealing. In future, we want to work on second species and third species and other species of counterpoint music generation. I hope you liked it. Thank you very much. Now over to Fabiola.
Thank you, Ashish, for your presentation. I'm going to pause this. Okay, so another goal of ours was to investigate how quantum annealing can help us tackle tasks such as music completion. So music completion is a term that refers to the generation of musical fragment from an incomplete segment of music. And our goal is not to replace the composer, but rather to assist him or her when creating their pieces by allowing them to use an algorithm that takes into account music conventions and other existing pieces of music. So we can offer suggestions that are aligned with their purposes. So that is why we decided to approach the common tasks to the composer, which are harmonization and melody completion. So in melody completion, we have supposed that the composer is generating a melody, and he or she, they may be they know what notes they want to use. They know the direction that they want to take, but maybe they don't know exactly which path to take to get from a certain note to another. And so, so in this case, we have thought that it would be useful to consider existing pieces of music because there are patterns in there that we could use as examples of the kind of music that they want to produce. And in the case of harmonization, we have supposed that the composer has already developed a melodic fragment, and he or she, they may want to start looking for the best options to accompany that melody. And so concerning this point, we have thought that a good strategy could be to follow the most common rules of music theory in order to develop a sequence of chords that goes well when played with melody. So our methodology is based on the use of a Markov network. A Markov network is a set of random variables, in our case, binary variables, that will form an undirected graph which satisfies the Markov property. So we are going to have a set of states, and these are going to be our vertices or nodes of the network. And each one of them is going to be related to the others by means of a parameter that we are going to be calling a potential. So the idea here is to encode our states and define our potentials so that the algorithm is able to find the configuration of the network that is going to output the lowest energy, and this is going to be our solution. And regarding a Markovian property, this is another way of saying that every state in the network is going to be influenced only by the states that are adjacent to it. As antecedents, we can mention a work called Algorithms Generating Music with D-Waves Quantum Annealer. This was a project submitted to the IQ Hack 2021 hackathon. And what the authors of this work did was to use a D-Wave markup network in order to generate a sequence of chords in music. They encoded some chords as states, and they assigned the random values to the potentials between them. And so for each step of the sequence, they run the algorithm, they selected the sample that contained only one chord. And this way, by running the algorithm several times, they were able to generate a sequence of chords. But in our work, however, regarding melody completion, we consider that the initial state is going to be the first note of the melody and the final state as a note that we want to arrive to. So therefore, our variables are going to represent the notes that we have available in the typical music system. So having that in mind, what we have to do is to set the values for the parameters that relate each variable with one another. And the graph features the way in which we define our system. We see, for example, that the first note of the melody can be the note C, and the second note could also be a note C or D or E or an F. Of course, in this example, we just consider 4 notes for simplicity, but in the actual model, we consider all the notes in the scale. And of course, we have to avoid having several notes played at the same time, and that is why the potentials relating notes to labeled as the first ones of the sequence will have to be very high in comparison to the other potentials. And for the potentials, we analyzed several pieces of music, including some of the inventions of Bach. And for that purpose, we used the Music 21 library, which is a fantastic tool that allowed us to analyze MIDI files and extract notes from the music pieces that we chose. And finally, in order to have in our solution the initial and final note that we chose beforehand, we set some constraints to the system. Here are some of the results we got. It is going to be an original melody. And the next one is going to be the melody modified. The notes in purple are the ones output by the algorithm. This is another one. And so now concerning the task of harmonizing a melody, our system is going to have as states the chords that can be constructed using each note of the scale as the root of the chord. And again, we can impose the initial and final chords. And also we have to set high values for the parameters that would represent having 2 or more chords played at the same time. In this case, we for the potentials, we chose values based on music theory. In this diagram, we can see, for example, that it is desirable to have a chord with the 4th note as the root, following a chord that is built upon the tonic of the scale. And the algorithm will scan the melody and input parameters only for the chords that contain the note in consideration. And in order not to have the melody overshadowed by the progression of chords, we decided to choose samples that contain only chords for the strong beats. And these are some of the results we got. And so in conclusion, we investigated how quantum annealing can help us to generate music and to what kind of problems it can be applied to. And for this purpose, we explored music reduction, counterpoint generation, and music completion problems. And we can conclude that quantum annealing can be an alternative to generate quantum music. And that would be all. Thank you all for attending this session, and thanks to the organizers for letting us be part of this great event. And I hope you found our work interesting. Thank you.
Okay, thank you so much. I think we have time for just one question. So for this one's for Fabiola. In the melody completion, can you take different scales into consideration as a constraint?
Different what? I'm sorry.
Oh, different scales.
Yes.
Okay.
We considered the major scales and the minor scales. Yeah, we can.
Nice. All right, great. I think we should move on to our next presenter, but thank you guys so much. That was an amazing presentation.